Before we move on to look at our more detailed algorithmic approach for determining system stability, I want to go over a couple quick ways that we can check to see if a system is unstable. So both of these methods we're going to be considering the denominator polynomial of our equivalent transfer function. So with the first sort of quick check method, what we're going to be doing is we're going to be asking, is the polynomial missing any terms? So is our polynomial missing terms? And so if the answer to that is yes, then that means our system is going to be unstable. There's also a chance that it can be marginally stable in this case, but at the very least, we could say that our system is not stable if it is missing terms. So what do I mean by is the polynomial missing terms? So let's say we have some polynomial in the numerator, so I'll call it n of s, some numerator polynomial, and in the denominator, maybe we have s cubed plus 5s plus 8, for example, just sort of picking random numbers. So what we notice then is that we're missing an s squared term. So because we're missing that s squared term, we can right away say that this system is not stable. It might be unstable or it might be marginally stable, but we know that it's not stable. The second thing that we can consider, so maybe it has all of the terms. So let's sort of adjust this. Let's say it has s cubed plus 4s squared minus 5s plus 8. So the second thing that we're looking for is to see if all of the coefficients in that polynomial have the same sign. So do all polynomial coefficients have the same sign? And so again, if the answer, well, different answer now, but if the answer to this is no, then our system is going to be unstable. So for this case, we have a coefficient of 1, 4, -5, and 8. So we have this -5 here, which has a different sign. And because of that, we would say that our system is right away unstable. So without even having to go into the detailed method that we're going to look at later, we could pretty easily tell if a system is unstable. However, one sort of word of warning is that neither of these quick checks are telling us that our system is stable. So let's try to do that a little better. So neither of these confirm system stability. They're just telling us if our system is unstable. So they just notify us of an unstable system. And so what that means is maybe we have a system where we have some numerator polynomial n of s, and again, I'm just randomly putting numbers, so I don't know if this is necessarily stable or unstable, but if we had, for instance, s cubed plus 4s squared plus 5s plus 8, we can't say whether or not right away that this system is unstable or stable or unstable. It doesn't meet any of the quick check criteria, so at the very least we don't know right off the bat that it's unstable, but we can't say for sure that this is stable. So can't say for sure this is stable. And so ultimately what that means is we're going to need that more detailed method a little later on. In the next video, we're going to take a look at what this sort of looks like with actual systems, but then we're ultimately going to come back and say we're going to take a look at how to approach this algorithmically to determine whether our system is stable or unstable.